Some attacks on routing protocols. As I indicated, in the early days of dynamic routing protocols, they were unauthenticated, and any bad guy could drop a router on a network and just start making announcements about bogus networks. And he would actually poison the route tables of all the routers and can hijack all traffic to his networks where he has sniffers and other sorts of monitoring information. In other words, he can steal all your information. He can denial of service your network by taking legitimate traffic off of your network and misdirecting it to his network. So these were the major types of attacks. In addition, you can also flood a router with too much traffic and cause that router to sometimes fail or at least not be able to accept legitimate packets in that particular port.
So now we're going to go over some MAN technologies, Metropolitan Area Network. And when I was talking about the difference between LAN, MAN, and WAN, it's not just the distance. It's actually the technology that is used at the data link and at the physical layer. So FDDI is a technology, a protocol that's been used over MAN links for quite some time. It uses token passing, which we talked about what token passing is, where token ring is a LAN technology. FDDI actually uses 2 tokens and can work at a higher speed. Now FDDI, that stands for fiber. Now the same technology can actually go over copper, which is CDDI. And the big difference between FDDI and CDDI is the actual length of the segments itself, because photons in fiber can go a lot further than electrons in copper, because the electrons in the copper have there's more like strain or it'll do attenuation. So really the big difference between them is how long or how long you can have your segments. So FDDI has built-in fault tolerance because it has 2 actual networks, so you can think of 2 circles. So this is the primary network, and the data will be going over that. And then if the primary link actually goes down, there's a secondary link that could take over and move the data. So it's built in with this fault tolerance, and it'll happen automatically. But some environments actually use both rings to move data at the same time. So if you do that, then you don't necessarily have that fault tolerance. But they do that because the second line is just there empty, waiting for a failure to happen. Now, a common thing that's used is called SONET rings, and you may have seen like OC dash a number. That's optical carrier dash, and then that number represents the actual bandwidth that can go over that fiber link. So a sonic ring isn't a technology that works at the data link layer like FDDI, but it is it works at the physical layer because it's going over fiber. But remember earlier I talked about signaling or encoding because SONET has a specific signaling. That's what it dictates. It dictates how the data is actually going to move over the fiber link itself. And in SONET rings, it doesn't matter what type of data that is being moved. And how you could think about it is a sonic ring would actually be like a highway. And a highway can have buses and cars and motorcycles. It can have a lot of things that actually go over it. The highway doesn't care. The highway is not going to restrict it. It's the same with sonic rings. You can move voice data, data, video, anything over a sonic ring. So they're used in MANs in metropolitan areas, and then they can be connected to WANs, a WAN link that needs to go farther and maybe connect to another MAN. So they're smaller than WAN, of course, and they'll use a different technology. Basically, if you need to go from a MAN, a metropolitan area network, to another one that's very far away, you'll be going over some type of wide area network technology that we'll talk about. the actual sonic rings connect to each other. Like you'll have a sonic ring can be like for, let's say, a town, and then all of the hospitals and ISPs and government, everybody connects to the sonic ring. And then you have another sonic ring, and the two are connected by a device, of course. And then you'll have another sonic ring maybe for the other town, and then you'll have another sonic ring for the other town. So they all are connected. Now, if you need to just, your packets need to go 2 towns, over, then it's just going to go through these MANs. If it actually has to go across, the world or across the nation or something, it'll go from a MAN to a WAN. And what happens is in a MAN, it will have a head device which will split the type of data it is. So if it's satellite data, the head will actually put it in the format of satellite radio frequencies. If it's wireless, it'll go over that spectrum. If it's voice, it'll go over that telephone network. If it's going over the internet, so at that head, it will determine and put it into the necessary signaling for the different type of data for the different network it's going over.
In this section, we're going to be looking at networking services, specifically domain name services, network address translation, and network information systems. First, we'll look at DNS, or domain name services. DNS is a service that translates friendly names that are intuitive to humans into IP addresses. We don't know the IP address of a particular server, but we do know intuitively the name of the server. So DNS allows us to use the friendly names that are intuitive to humans and will translate that friendly name into the IP address that's required for connectivity in the background. This is all hidden to the end user. It uses a hierarchical naming structure such as www.careeracademy.com. The .com is called the top level namespace. Career Academy is the second level or tier 2 namespace. That's the specific entity or corporation. And the www represents the specific server or the host name for the server that is the actual target of the request. Again, it translates fully qualified domain names into IP addresses. These addresses and names are recorded in what's called a resource record that gets stored on the DNS server itself. So every computer is a DNS client to DNS servers, typically more than one for fault tolerance. As I indicated, the DNS system uses a hierarchical naming structure. The top of this naming structure is referred to as the root. There is no actual name associated with the root other than root, and it records the locations or the IP addresses for all servers at the top level namespace. So there is a .com server, a .edu server, a .gov server. The root servers, and there are 13 of them on the public internet, the root servers hold the IP addresses for the top level namespace servers like .com, .edu, and .gov. If your query is for www.careeracademy.com, your query would first start at the root. And the root would say, well, he's looking for a .com server, here's a .com server. When your query reaches the .com server, the .com server would hold the IP address of the name servers for Career Academy. You then would be connected to the name server that holds the namespace for Career Academy and query for a specific resource record for www. This is how you would then get returned the IP address of the specific web server that you're looking for. So this all begins with a client that is a DNS client. A DNS client is referred to as a resolver. The resolver is configured in its IP properties with the IP address of a DNS server that is going to be responsible for resolving all names for this particular client. So anytime the resolver asks for a fully qualified domain name, in the background, the TCP/IP stack will go query the name server, or DNS server, that is configured in the IP properties for that resolver. Now the problem lives with the DNS server. So the resolver is asking for www.careeracademy.com. Well, the name server doesn't know that information. So the name server goes out to the internet and talks to a root server and says, hey, root server, I've got a guy down here, a resolver, that's looking for the IP address of www.careeracademy.com. The root server doesn't know anything beyond the .com, .mil, .gov, and he says, well, the best I can do is redirect you to a .com server who might be able to help you further. Your name server would then query the .com server that was provided by the root server. And the query would be for www.careeracademy.com. Well, the .com server doesn't know the www part, but he does know the Career Academy part. So he says, hey, name server, I know a guy who holds the namespace for careeracademy.com. Here's his IP address. Go talk to him. Your DNS server now would go talk to the name server that holds the namespace for careeracademy.com and query for www.careeracademy.com. That server would look at the resource records, identify the next www record, and then would return back to you the IP address for www.careeracademy.com. That information then would be cached by your name server for 60 minutes by default, and then that name server would forward that IP address back to you, the resolver, so that your web browser could now connect to the web server, www.careeracademy.com. A couple of important things to note here is the resolver's query to his name server that's configured in his IP properties. That is called a recursive query. A recursive query is a query that says, hey, name server, go find me this IP address. Don't redirect me to anybody else. You come back with either the IP address or tell me the name can't be found. Don't send me anyplace else. That's called a recursive query. So resolver to DNS is a recursive query. Now, your DNS server, when he realizes he doesn't know that name and has to go out to the public internet, talk to the root servers, he issues what's called an iterative query. He will get small pieces on the trail to finding the correct answer. And he'll first go to the root server will reply back with a COM server. Then he'll go to the COM server will reply back with the careeracademy.com name server. He'll then go to careeracademy.com and actually get the resolution for the www record he's looking for. That's an iterative process. So you have recursive queries, resolver to DNS, and then you have iterative queries, DNS to the public root system, the DNS system in the public internet. So we have recursive queries and iterative queries. You should know the difference between those two. In most organizations, you will have internal DNS so that on your corporate LAN, behind your firewall structure, on the intranet, you will be able to identify and locate servers, clients, and services on the corporate intranet. Those are internal DNS servers. In addition, you generally will have public DNS servers as well. These are servers that are available and exposed to the public internet so that public clients can find your web services such as HTTP, SMTP, perhaps even FTP and others. So you will have two different DNS systems. One is publicly exposed and will only hold a few records and be very hardened and very secure. And then we'll have internal DNS to provide internal name and service resolution so that we can function on the corporate network. This is referred to as split DNS. Some attacks on DNS include web spoofing and DNS poisoning. These are two very different things, and students get confused by these. They think one is the other. One leads to the other, and we'll talk about this in just a second. Web spoofing is where a bad guy will actually clone a legitimate website on his server and make it appear exactly like the original legitimate web server. His whole point of doing this is generally to steal private information about the browsers that connect to the website. Then what he has to do, that by the way was web spoofing. Once he gets this website set up, what he has to do next is he has to attract clients to that bogus website, the spoofed website. And to do that, to get clients to that spoofed website, he will poison the DNS system. This is one of his approaches to attracting clients to his spoofed website. And the way he does this is he will actually poison the DNS server with the incorrect IP address, that is the IP address of his spoofed web server, for the legitimate website. In other words, let's say www.careeracademy.com lives at 100.100.100.100 IP address. That's the legitimate website and the legitimate IP address. What the bad guy will do is he will clone the www.careeracademy.com website. He will build in his malicious code, whether he's stealing information, whether he's pumping down malware onto your computers, the browsers that connect up to it. He'll build his malicious content into that website. But then to attract the clients, he will poison DNS and say www.careeracademy.com lives at 200.200.200.200, the IP address of the spoofed web server. So now legitimate clients querying for www.careeracademy.com will be returned from DNS the wrong IP address that will take them to the malicious website. This is DNS poisoning, is the attack on DNS. Web spoofing is the cloning of the legitimate website and the introduction of the malware on that spoofed website. In this diagram, what we see is the attacker would first clone his spoofed website, and we see this at the very top of the diagram. This is the false website with the malicious software installed on it and configured on it to either steal your data or poison your machine with malware. That's his first step. He has to build that spoofed website. Then what he has to do is he has to attract clients to that website. So now he will go attack the DNS server. He'll inject his record into DNS. It says when you're trying to go to the legitimate website, give them the spoofed website's IP address. And now when a legitimate client goes looking for the legitimate website, he gets the IP address of the spoofed web server and will arrive at that spoofed web server unknowingly, might provide his private information, credentials, credit card information, whatever, and or might also be infected with all sorts of malware from that malicious website. So this is actually two different things. First we have web spoofing, that's the cloning of the website with the malware, and then we have DNS poisoning, that's the vehicle that is used to attract the clients to that spoofed website.